All right, today we're diving into something really cool. A brand new way to predict the weather, but not here on Earth. We're talking about the weather in the vast, empty space between us and the sun. Scientists have come up with this incredible method to model our star's gigantic, invisible magnetic field. So how'd they do it? How do you build a virtual sun? And what can it tell us?
I mean, think about it. It's a huge challenge, right? The sun's magnetic field is this invisible force that dictates a constant flood of particles, what we call the solar wind, that fills our entire solar system. If you want to understand space weather, you have to map this thing. But when it's invisible and stretches over 90 million miles, where do you even start?
Well, the answer is you built a digital twin. This amazing picture you're looking at, that's not a photo. Nope, it's a supercomputer simulation, a virtual sun that shows us the incredibly complex structure of that magnetic field as it twists and swirls on its way to Earth.
So to really get how they pulled this off, we first need to understand the basics of how the sun's magnetism really shapes our little corner of the universe.
For a long time, our best guess was a pretty simple idea called the Parker spiral. Just imagine the sun as a spinning garden sprinkler. The water, or in this case the solar wind, shoots out in a straight line. But because the sprinkler itself is turning, the stream makes a beautiful spiral pattern. And that's basically what we thought the sun's magnetic field looked like. Simple enough.
But here's the catch. The sun isn't always a nice, steady sprinkler. It has this 11-year cycle. When it's quiet, during what we call the solar minimum, its magnetic field is simple. And yeah, the Parker spiral model works pretty well. But during solar maximum, the sun is a whole other beast. It's an angry, chaotic mass of sunspots and tangled magnetic fields. And when that happens, our simple little models, they just completely fall apart. They're useless.
So, to solve this puzzle, researchers needed a much more powerful tool. They needed a real space weather forecast.
And that tool is called magnetohydrodynamics, or MHD for short. It's the wild, incredibly complex physics of how magnetic fields and superheated plasma, like the solar wind, all interact. Basically, it lets scientists do for space what meteorologists do for hurricanes here on Earth. They run all the physics through a supercomputer to create a forecast for the whole solar system.
So, how's it work? It's a pretty brilliant four-step process. First, they start with what we can actually see, real historical data of sunspots. That lets them build a magnetic map right on the sun's surface. Step 2, they take that map and kind of blow it up, projecting it outward to create a virtual bubble 10 times bigger than the sun. Then, at that new boundary, they use known physics to figure out the speed, density, and pressure of the solar wind as it crosses that line. And finally, the fun part, they plug all of that into the simulation, hit go, and let the supercomputer calculate the entire journey, all the way from the sun to us.
And the results? They are absolutely stunning. Let's take a look at what the simulation spit out for a quiet sun versus a really active one. Okay, so these are the starting points they fed into the model. On the left, that's the sun at solar minimum, back in 1987. See how clean and orderly that is? Nice, neat bands of magnetic polarity, almost like a simple bar magnet. But now look at the right. That's solar maximum in the year 2000. It is a completely different animal. Just a chaotic jumble of positive and negative magnetic spots splattered all over the place.
And right away, you can see how these two starting points are going to create completely different outcomes. The quiet sun on the left, that's going to produce a pretty predictable solar wind. But the active sun on the right, well, that's going to unleash something way more wild, way more turbulent.
And here it is. This is the big reveal. Look at the left, the solar minimum simulation. It creates this beautiful, relatively flat, gently waving sheet where the north and south magnetic fields meet. But on the right, wow, during solar maximum, that sheet gets twisted and warped into this monstrously complex shape. It's no longer a flat sheet, it's a chaotic mess. It's the difference between a calm pond and a raging waterfall.
Now, let's follow that wind all the way out to Earth's orbit. These maps show the predicted space weather right as it gets to our neighborhood. Check out the left side, during solar minimum. You see these smooth, predictable bands of wind speed. Now compare that to the right. It's a turbulent, splotchy mess. You've got these unpredictable patches of fast winds slamming into slow wind. It's pure chaos.
Okay, this all looks incredibly impressive, I get it. But let's be real for a second. It's a computer model. How on earth can we know if any of this actually reflects what's happening in reality?
Well, you check it against the real thing. You find actual data. This graph here shows real measurements of the solar wind.
taken by a spacecraft called IMP-8 way back in 1987, the exact same quiet period they simulated. You can see these huge spikes in wind speed, getting up to 700 kilometers per second.
And here is the smoking gun. The model predicted something really weird, a stream of super-fast solar wind right near the sun's equator, which nobody expected during a quiet period. But as this quote from the paper confirms, when they went back and looked at that old spacecraft data, boom, there it was, the exact feature the model predicted. The simulation didn't just get the basics right, it predicted a strange, unexpected detail from decades ago. That's how you know you're onto something.
Okay, so the model is legit. It works. But so what? Why is this so important? What does it actually mean for us?
This is way more than just a cool science project. You see, the sun can throw these violent storms, called CMEs, at us, and they're powerful enough to knock out satellites, mess with GPS, and even take down power grids here on Earth. To predict those storms, you first have to know what the background weather is like. This model gives us that crucial baseline. It's a fundamental new tool for forecasting space weather and for protecting our technology and our astronauts out there.
And here's what might be the coolest part of this whole thing. Because the main ingredient for the model is just sunspot data, and we have really good records of sunspots going back for centuries, scientists can use this to run the simulation backward in time. They can literally reconstruct the space weather environment for the last 300 years, giving us a detailed history of the sun's magnetic personality.
So this virtual sun has given us an incredible window into our star's past. The real question now is, as we get ready to go back to the moon and on to Mars and even further, what will it teach us about navigating our future?